All right. Better. So SOC trends, and particularly SOC trends as they apply at TI, I've got this graphic across the top. Now, this is not a chip roadmap from TI. It's not in chronological order, nor does it necessarily represent any particular chip that we have. But what it does do is it represents the transitions and difficulty in dealing with multiple devices. So we went from the good old days of one core, I'm sure all of you might remember that, to going to a homogeneous multi-core environment, to going to a heterogeneous multi-core environment, and from then going into what I call various multi-core, which is many disparate devices on one chip. Okay. I was banned from all further marketing actions because I previously had the word multifarious multi-core, which multifarious simply means many and varied, but they said nix that and just go with various. The power and performance in the area, an area being a proxy for cost, can clearly be optimized by specialization and replication in this manner. I think the business case is clear. I'm not going to go into that. You've seen many instances of heterogeneity in previous talks. And of course, the cost is clear too. Software complexity rises, the need for having greater developer skills goes up, and frankly, the portability of your applications goes down as you're trying to move across these types of chips and architectures. So the goal is, obviously, we want to be able to maintain the PPA advantages of these architectures, and we've chartered my team with not eliminate, but to reduce to the extent possible the costs that are associated with this. So what are some things that we have done, or what has been our history here? So in the transition from single core to multi-core, OpenMP made perfect sense. Okay, I don't know, most of you I'm sure are fairly familiar with OpenMP, but it's pragma-based. You can iteratively parallelize your application. It does have the benefit of once you've done that with OpenMP pragmas, it can be backward portable onto a generation that was a single core device. Now, that sounds all great, but if you've ever gone from one core to two cores, you know that that's a difficult transition. Even though the expression is easier in OpenMP, you still probably are going to have to restructure your code. You're going to have to make it enabled for multi-core, dealing with mutual exclusion, so on and so forth. So we put our internal developers and our customers through this transition where they went through this process of rewriting their code using OpenMP. Now, when the next transition came along and we introduced heterogeneous multi-core, we put a CPU down on the chip. It was obvious to me, and perhaps no one else at TI, that OpenCL was a potential here. And we embarked on an effort to port OpenCL onto our very deeply embedded chips and then to spread the word that that's how you're going to program it. And while we thought that was a brilliant idea, again, I think we were the only ones. The rest of the community in TI, full shields up, speak to the hand, you name it, that's about the response that we got from that. And primarily the reason was they were concerned about their existing code, okay? They had already gone through one rewrite to go from single core to multi-core. They didn't want to have to do another one to get to heterogeneous multi-core. Now, I think the thing they were missing was if they were going to take advantage of the heterogeneous multi-core, they were going to have to do something anyway, right? But you know, nevertheless, it was hands up to us. So what we did is we engaged with them and we asked, you know, what could we do that would grease this process for you? And they asked about us dispatching from the CPU code that already had OpenMP embedded in it. They talked about being able to do resource allocation from within kernels that were being dispatched from the CPU. Because if you look, the multi-core situation there where you've got the multi-core DSPs, that was a full application. I mean, it's linked, they're doing resource application, it gets loaded and run. And for all intents and purposes, what they were asking us to do was take that, dispatch it from the ARM and let it run unmodified as one use case. Okay. So they rejected pure OpenCL and we listened, and so we went and did a few things to help grease the skids again to get them to port their code. And I'll go through two of the examples here. So we allow OpenCL C code to call out to standard C code. Okay. It wasn't very difficult for us. The DNA of our OpenCL C compiler and our standard C compiler are 90% shared anyway. So interlinking those types of binaries was easy. We did have to deal with the fact that, that the C code might have OpenMP in it, and I've got a slide on what we did there in a moment. The other thing that we did is we gave them a real easy means of doing their own dynamic heap allocation on the devices. Okay, and I have a slide on that as well. So OpenCL C calling standard C, it's rather trivial in concept here. At the top there, and I have the C++ bindings in all my examples, but in the top there I have a string representing the kernel. It's calling out to a function called alg, which is undefined in the OpenCL C code, and the reason being is it's a standard C function. All right, and the way that we deal with resolving that symbol is when you go through the standard build API call for your OpenCL C source, we've extended that to where the string is where you would normally put your options. You can put your options, and you can also optionally put object code, libraries, whatever you want there, okay? And that object database can then be used to resolve unresolved symbols in your OpenCL C code. We could have used OpenCL 1.2 separate compilation here. Our implementation is 1.1 compliant. We didn't, primarily because we wanted to be able to use the 1.1 C++ bindings unmodified. Didn't want to cause conflicts there, and not only the C++ bindings, but the entire ecosystem that can sit on top of a conformant OpenCL implementation. And then if the C code has OpenMP pragmas embedded in it, the way we deal with that is, and the reason this is a problem, well, actually let me just get to the slide. The reason this is a problem is that if the OpenCL runtime is completely unaware of the fact that your C code has OpenMP embedded in it, we didn't want a resource conflict with OpenCL runtime trying to manage the compute units in our system and OpenMP orthogonally trying to do the same thing. So we have a very simple method here is if you dispatch a kernel that is one work item or a task to a queue that is defined to be an in-order queue, the way that will get handled by our runtime is it will run by itself on one compute unit while the other compute units are idle. That was actually viewed to be a downside of an in-order queue in a task, but happily it turned out okay for the case where you've got a C code being called that's got OpenMP. If we do that, we dispatch an OpenCL C kernel to one compute unit, which is just one DSP core for us. Then the OpenMP runtime could kick in and take you wide with a fork and go across all of the cores. And that works out very well for us. The other thing is being able to do malloc and free. Again, these applications were doing their own memory management. We do have a standard sized heap. It's very limited in size. If they just wanted to do a standard malloc and free, they could do that. But if they wanted to be able to do a malloc and free, in other words, if they wanted to have a heap of a significant size, we had a couple of choices. We could have partitioned our global memory. Here's heap space that you can allocate from the device. Here's memory that's being managed by OpenCL. Clearly didn't want to do that because I didn't want to statically partition that memory. The other thing that we could have done is having either host or DSP send messages to the other when they wanted to do allocation. I didn't want messages to be involved with the allocations either. So we came up, this is really just a hack, but it works, and this actually was something that was accepted by our developers, is you pass a buffer into a kernel, and then we provide you a handful of extended built-in functions that you can use to initialize that buffer as a heap and then do mallocs and frees out of that heap. Very simple, very easy, solved the problem. We didn't have to change anything within OpenCL other than adding a couple of extended built-in functions. We actually have 3 memory ranges in our implementation. There's global memory that goes to DDR by default. There's local memory that goes to L2 by default. We also have another area of memory it's an on-chip shared memory. We map that as a global memory space that's tagged with an extra flag. This is how you define a buffer in it. You define it just like a global buffer, but you give it our special tag. So we gave you built-in functions for all three of those memory ranges. If you create a heap in DDR or in MISMIC, it's persistent for as long as the buffer is undestructed, as long as it's valid, okay? So you could have kernel after kernel with persistent data in that heap. L2, not so much. Its lifetime is the extent of one kernel in Q. Okay. So this is, probably this room gets this slide, or will get the slide once I put a little bit of words behind it, but something that I constantly ran up against when I was trying to convince people that OpenCL was an opportunity for us to reduce software complexity. All right, I think most people think OpenCL is a way of increasing software complexity. And the way I rationalize that to everyone else, and I'm going to share it with you here, is it depends on your frame of reference. If you are a CPU programmer, you don't necessarily involve yourselves in the hardware details, then clearly adding OpenCL is a complexity to you, but you wouldn't do that unless you were involving another architectural element. And so I've split the two out. It is the fact, in this case, we don't have a GPU in our system, or at least not all of our systems, but I'm going to use that as the common case here. If you've chosen to go from one architectural element called a CPU to two architectural elements, one a CPU and one a GPU, it was the fact that you put that other architectural element into your system. That was the add of complexity, okay? OpenCL then on top of that is a reduction of that complexity, okay? If you were to deal with that heterogeneity and the low-level drivers and the IPC going back from the CPU to the GPU and so on and so forth by hand or at the very low level, that's far more complex than doing it in OpenCL. So I rationalize and I'm firm on this, OpenCL is a reducer of software complexity, okay? How am I doing on time, Ben, given that we started late? Okay, all right. I'll go really quickly through this. So I had the transitions from single core to multi-core to heterogeneous multi-core earlier. There was one more note on that slide that was the various multi-core, where we had many elements that were quite varied in their capabilities. And OpenCL custom device, and frankly Spear, I failed to put Spear down on the slide. But the combination of those two, I think, actually helps us even in this circumstance. And so just your decoder ring here, I'm sure you get CPU and DSP and GPU. MuC is a microcontroller, very much like a CPU, except there's clearly not going to be any floating support on it, minimal resources. It can be generally programmed, just not to the same level as OpenCL requires. The next one down the hierarchy here would be what I call the DSE. I actually wanted to call it domain-specific processors, but then that would have been DSP. That would have conflicted my other use of DSP, so I called it domain-specific engines. So these are things that do very specific things. They are programmable, but they're not programmable to, say, a C level. You can program them with a domain-specific language. And then at the bottom of the hierarchy here would be some kind of hardware IP block. You don't program it at all. It's got fixed function, okay? And a very complex, deeply embedded SoC might have a combination of all of these on there. And to be honest with you, I'd love to be able to bring to bear the concepts of buffers, sharing data through a buffer, the event mechanism that OpenCL allows, using all of that to build, for example, in the last graph, talk you saw that nice graph where he was using events to define that. I'd like to be able to do the same thing where the execution of some of those blocks is done on these varied multi-core devices. All right, and then lastly, the execution model. So at least in the 1X time frame, the OpenCL execution model is very much a master worker model. Okay, it's host-centric. He's responsible for control. He's responsible for data availability and so on and so forth. I'm okay with that. We've been able to engage new users that were CPU-only type users by using OpenCL as it exists today. But the very, very hardcore embedded programmers, they don't program like that, okay? These devices have data paths through them that don't even go to the CPU, okay? And so this is an example where you may have a sensor array, it's plugged directly into some unit, and then we've got a pipeline stage through the chip to get to an output, okay? So typical embedded, when you add real time on top of that, and I've got a signal showing up on a very defined interval, and it must be handled or lost, this pipeline model makes a whole lot of sense, and I need time guarantees, okay? So what to do? Well, even in a 1.x OpenCL implementation, if I break that control and data availability lines from the host down into the kernels into two, one's control and one's data availability, I can already solve the data availability, okay? The data does not have to, in our system, because it does have shared memory, it does not have to travel back and forth to the host, okay? I can have kernel writing to a buffer, that buffer persists in the shared memory, the next kernel can then read that directly, and so that helps, okay? And then the last remaining piece of the puzzle is the control, okay? Now, OpenCL 2, and we heard a lot about OpenCL 2 this morning, have added a number of features that are directly aimed at this data flow problem. Pipes, in my view, shared virtual memory is a help in general, but then fine-grained virtual memory with the memory ordering rules and the atomics in particular, I think, can help this problem. And then device-side kerneling queue as well, okay? The problem is, and I don't have the solution yet, so this is next time, but our data flow, all of those features, at least to my understanding, all of those features were added for data flow within a device. I've got data flow across these devices, okay? So I might have, in that previous picture where I had those stages, each box in that stage could be on a completely different device within our SoC. And I think we could do that today, perhaps somewhat orthogonal to the OpenCL implementations, but what would be nice and what we're going to look at in the near future is, can we do it in the context of OpenCL proper? And that's all I've got.
Thank our speaker. So maybe let's do we have one question? Yeah.
It better not be a question about how do you get a presentation up on the screen.
No, it's actually a comment. We have exactly the same issue where we want our devices to talk to each other, FPGAs.
Yes.
And we are using a vendor extension, but we would more than love to work together with partners like you to come up with a proposal for Kronos to just standardize this.
I think that would be wonderful. That would be wonderful. Let me drop you a card before I run out the door to the airport. So, thank you.
Okay, so we're over.